Hello everyone, let us start with the following lecture that covers the important topic of system representation given in a continuous domain by a system of ordinary differential equations. In other words, in state space form. So we have a state space form, which is given as usual with the matrix A, B, C, but I will write in explicit manner the explicit structure of the system where A, B, and C matrix are present. And we consider that all these x and y and u are functions of time, and we want to look what other representation of this system we can have. This form is differential form of the state space, differential form. Or in other words, we call ordinary differential equation system, I will write all these, this is linear system where A, B, C, and D are matrices with a constant coefficients. Besides this differential form, and this lecture is specifically looking into another, it's integral form. Integral form of the system representation. So we want to find out how we can transfer from this differential into integral form. In other words, how this integral form essentially looks like. So I will just put the question mark. Let us consider the example of a single tank, and we are going to use this illustrative example. First, we are going to write the model of the tank. Here we have a valve. Here we have a flow. And here we have some other flow that is coming into the system. And essentially, this is F1 of F input. This is F output. This is F U. And this is the overflow in this realization of two flows coming together while one flow first is filling this tank, and again it gets summed with another flow line and generates the f of t. The simplest system of differential equations that describe the dynamics of this system are given, and we know already that is given as A, which is the surface of this tank, multiplies dH by dt, input minus output, where this is F1 of, or Fi of t minus F out of t. And here we have an output equation. F of t is equal F out plus F u. In other words, if we just apply what we already know, and that's that there is a linear characteristic that relates the height of this tank and this flow. F out, I will just specify here, F out is equal by H by K. We will have the following representation of the system, and I will just write everything in the form of standard state space representation, where I'm claiming that H is equal X minus 1 by K by AX plus 1 by A, and this is F in of T, Y of T, or F is just 1 by K X plus 1 multiplies F U of T. So we identify here these coefficients. This is the coefficient that here is the coefficient next to the state, and this is the B matrix, this is the C matrix, and this is the D matrix. Now, if we want to obtain the integral form of this differential equation, let us look how we are obtaining that, and let us rewrite the first equation. Here I'm going to call this equation 1, and this is going to be equation 2. I will rewrite this equation in a simpler form, just x dot equal a of x, where coefficient a is just a is minus 1 by ka here, and plus b u of t. I'm just claiming now that this is the equation that we are working. U of t is f input of t, and in order to obtain integral form, let us take this equation and multiply by e to the minus a of t. So I'm multiplying this equation, so we obtain e to the minus a of t x dot of t, and let us transform ax of t from this side to the left side, so we are getting a to the minus a of t ax of t, and here we have a to the minus a of t b u of t. Okay, the next step is to recognize what is this expression on the left side. And one can claim that this expression on the left side is nothing but if we take the differential of the following expression, d by dt of e to the minus a of t x of t. Just work it out. So if you take differential, this term will generate this term, and then x dot of t, you will have like a differential of the function x1, x2. So in other words, this term is obtained by differentiating the second element in this bracket. So this is what we have. Now, if we integrate this expression from t0, some initial time, to t, what we have, we will just integrate from t0 to t dt, and here we also integrate from t0 to t, but now this cannot be t, this has to become tau, this expression. So here I'm just going to make this tau. I'm just going to make this tau, and I'm going to make the tau, because this is essentially dummy variable. Integrating the left side of this expression yields that this dt and this dt will just get cancelled. Think about like that. Therefore, you have integration from a to b of function df. But what is that? That's f at evaluated at b minus f at evaluated at a. In other words, this expression will become as follows: e to the minus a of t x of t minus e to the minus a t 0 x at t0. And we keep expression on the right side intact. t0 to t, and this is e to the minus a tau b u tau d tau. Now, if we multiply this expression and we flip this to the opposite side, we will obtain that x of t is e to the a t minus t0 multiplies x at t0 plus e to the a of t t0 t e to the minus a tau b u tau d tau. So this expression, this last expression, is just obtained by multiplying this entire expression by e to the a of t. And now, since this function, its function of t, it can go into the integral, so that finally we obtain that x of t is e to the a t minus t0 x of t plus t0 t e to the a t minus tau b u of tau d tau. I'm just rewriting this. So this is b of t. Therefore, we got an integral expression. Finally, all of this is an integral expression of differential form here that we have. So this was differential form here, and we obtained the integral expression of this form. This is very interesting because we will be able to say that evolution of the x of t state is contribution of two parts. Contribution of the initial condition, this is essentially this entire part, where x of t0 is a state at t0, and some contribution that comes from the input here. This is function that is u of t. This is very important to realize that every differential expression will always have the integral form that we can utilize for a nice closed form expression of the evolution of the state x of t. Therefore, integral and differential form are the two forms that we are going to use in further studies.